just affecting the...
This is X.
This is X.
We are calling it disease X, so that we avoid the jargon part. So all we need is just a study design.
But you asked about how many people you're going to recruit.
Yes.
So I'm asking if the disease is zoonotic or it's...
We don't know whether it's zoonotic or not. We're just interested in, is there a tick-borne disease? We're going to use a particular method that can give us many diseases at the same time. And then we are interested in finding disease X. Disease X basically is the next emerging disease.
It will depend on the population.
Let's work with the Nyong virus. Let me use that. So we're going to use the Nyong virus. Now that's so that it makes it clear. It makes it easy. Nyong virus. Sound. Let's work with that. All right, now start. Now repeat now everything. Now. Now, so let's use, I'm using a virus that many of you are not familiar with so that we don't get stuck on the virus. Onyang virus is a virus that is transmitted around. It's a zoonotic disease. We have found it in a few populations, especially in certain areas that people have febrile illnesses, but we are looking for non-febrile diseases. So you go to a hospital and you have malaria, they will start with malaria and then come to typhoid, and then they will never go into like tick-borne diseases. So let's use that. You wanted the name of a disease. I've given you one. So we have like 5 minutes remaining on this particular part. So
what exactly are we doing?
How many people will you recruit?
Okay. This is what I will do.
Wait, they can't hear you. You think you're loud.
Okay. Now, in that particular county, I can map out the population of people. Then, based on the medical records, you can be able to tell a particular age group that is commonly infected by that virus. So going further, you can still, so to say it's a virus that has been identified among mothers. So you would know if you are conducting this study in Garissa County, for example, you can get the population of mothers. Then in your study description, you will have known which age group you are interested in. So you can apply a sampling formula to get the sample size.
Okay. So she has mentioned something about mapping the population. At the same time, she's also talked about sampling formula. So, you have the other pen, the blue one. So remember we are discussing cross-sectional studies. So we have Z, you can see this, this is D squared. So how many have seen this formula before? Lift your hand properly. I want to see you guys because I know a few of you that have worked with you. So, sorry? It's very faint. I write better in Word. Is that better? Z squared PQ divided by D squared. I'm going to point on a few people here to explain a little bit, and then now we build on it. So we're trying to calculate a sample size. And it's normally dictated by a few things. Ngetich, what is Z? Yeah, I know it's 1.96. So what is Z? The statisticians here, what is Z? Yes? The confidence interval that you want to get the results. Okay? It's the Z score at a certain confidence. Z-score at a certain confidence. I'm not going to go into what Z-score is because we'll go into a rabbit hole. But it's a Z-score at a certain confidence. You know the figure is what? 1.96. 1.96 for what Z-score? 95%. So, confidence interval. What is a confidence interval? The reason for this particular training is, one, as much as we're building knowledge, we also want to understand what it's doing. I've seen students plug in figures, and I'm happy for you to plug it in, but I'd like you to understand why we sample 200 and it will be a sufficient study, or like in my PhD, I sampled 165 households, and it was a sufficient study with certain corrections because of cost. In most times, you'll go for 400 or 300 something, right? So you can sample a certain number as long as you can explain it in your paper. So what is the confidence interval? Is a range by which your estimate lies. Can I throw a spanner in the works? What is an estimate? Epidemiology is a very interesting course in that every single thing can be a question in an exam. Estimate is? The values you use when you're making an inference to the rest of the population. Hold on to that thought. I'll come into that. What is P? Eh? Have the confidence. Proportion of a population with the outcome, also known as prevalence. We are building on every day. So, and prevalence was what in the cells? Probability of disease positive, right? Which was now what? A plus C over N. It's one probability of disease, not given. When it's given is when now you start doing the A over something else or the C over something else. Remember that. We are building on that. So this is probability of disease positive. So I'll call it prevalence. So then what is Q? 1 minus? Just say it. Don't we define say. So it's 1 minus. So what is 1 minus probability of disease positive, or what is 1 minus prevalence? Say it. Have the confidence, say it. There's no wrong answer. It's a discussion class. What's actually a compliment? So, is the disease-free proportion of the population. What does it tell you? Why are you multiplying the diseased portion and the disease-free portion? I know it's a formula that was made there, and we use it every day, right? But now, why would you want to multiply the disease and the disease-free proportions of the population? To confound us. What's your story? How many of you did probability in high school? How many of you did probability in high school? Okay. How many have heard of, okay, so let's do basics. When you have done, you can do additive, right? Probability of A plus probability of B is equals to? Probability of A plus probability of B is equals to? A union B. Are you sure? Probability of A times probability of B is equals to? A intersection B, which is other word is? Probability of A divided by probability of B is equals to? People always ask, utaitumia wapi? This is where it's coming. This is where it's coming. And this thing is on. So all this is based on probability. I don't want to go through the whole thing, but at a certain point, I'm going to go through it before we finish this particular lecture series. And the reason I'm saying that is, ask yourself, what are you doing? Because as much as we are using notation, P and Q, remember, this is a probability of D plus, right? Disease positive. And this is the 1 minus disease positive. So, and then what is D squared? Sorry? An? Allowable error. Where do we get it? Where do we get it? You have the answer. If you're using 95%, the error is 5%, right? So I would like you to not just plug in these things, because sometimes I see master students, PhD students, they just plug in the numbers and they're good, which is fine, but having a kind of a theoretical background behind it. And that's why I say, go back to probability kidogo. It helps a lot in terms of playing around with stuff. So Z squared is basically 1.96, which is basically the score at 95%. If we change it from 95 to 90, the figure changes, and this one also changes. Now, you are sent a folder kwa email, me download, called day 2. Mtakuwa nazo mingi. Called day 2. There is analysis and interpretation of data. Analysis and interpretation of data. Bwana, sijai kuwa na shida ya matamshi wewe. Are we there? Can we move quickly kidogo so that this was just something I added in there for the purposes of conversation. Okay, cool. You've opened that R code? Yeah? Everybody has it? No. The R code. The PowerPoint ndio hii hapa. Ama you also want to read on yours? I'm making your work easier. So open the R code. So, we are going to do this, then we'll do another class and move. Is everybody comfortable? Okay, let me ask the question. Does everybody have the R code open on R Studio? R Studio.
Just click the 3 dots, open R Studio.
So, we have done this today, right? We have a study design, and we have methods of summary, whether the cases are incidences or prevalences, and then what is the preferred measure of association. Cohort studies. Hello, focus Pandei, because we are going to go into something else. Cohort studies, we start with non-diseased sample, excuse me, and then we determine exposure, which is a follow-up over time. Is that clear enough? Incidence is what we get from that. We either do a risk ratio or a rate ratio. We are cool with that? RCTs, what is an RCT? Randomized controlled trial. We start with non-diseased samples, assign exposure, follow up over time. We also get incidence. RR, case control. We start with diseased cases, recruit comparable non-diseased controls, and then look at the previous exposures. We get a prevalence, odds ratio. We cannot do a risk ratio on this. You remember the conversation we had? And then we have a cross-sectional study, is what we're discussing now. From a sample, we assess both exposure and disease status. At the same time, we get a prevalence. We can get an odds ratio, which is normally what we use. We are good up to there? I think I've worked on that. I just wanted to show this because we're discussing cross-sectional study. We get a target population. Please see the photo. We get a target population, and we extract a study sample or a study population from it. You get it? We get a target population. We have a bigger population, right? And then we have a target population, and then we extract a study population from it. For cross-sectional studies, we are gathering data at one time on both the exposure and the outcome. So we end up measuring exposure and outcome present, 4 potential outcome things: exposure and no outcome, unexposed and outcome present, unexposed and no outcome. Please take note of that. Remember the 2x2 table? Disease positive, disease negative, exposure positive, exposure negative. Some people will be exposed but no disease. Some people will not be exposed, but they'll have disease. So it looks like that. We can draw this for every study design. And I always say, for you to understand what you're trying to do, when you go back home and you're taking time and reading like case control data, draw something like this. I've attached in that particular folder a small document from Oregon State. I'm not going to go through it. I'm hoping you can go through it. It has all this kind of, I took this from there. So it has all this that you can go for every study design. We have our formula, right? Where we have just discussed it, right? So it's z squared, we know what it is. We have p, which is prevalence, right? And then 1 minus prevalence divided by d squared, where n is the calculated sample size, z is the statistic that defines the level of confidence required. 1.96. P is an estimate of the key indicator being measured, the outcome, by the survey in the population, group of interest. In this one was prevalence of iron deficiency in women of reproductive age, expressed as a proportion of that population. 0.5, 0.6. 0.5 means 50%. 0.6 means 60%. And then D is the desired level of precision or the margin of relative error to be obtained. We are measuring the level of confidence at 95%, which means the error is 5%, right? We can measure it at 90. We can measure it at 80. But you need to have some justification for why you're doing it. In that code, okay, let me say, let's assume the prevalence of Onyong virus in Marsabit. Remember the example you gave, You know, we are still working on the thought process, In that code, go to that code. Go to step 1. You've seen where step 1 is? Where the first formula is? So let's assume the prevalence of Onyong virus in this particular population is 50%. So if you see that code, there's Z 1.96, right? Squared, That is what? Hiyo mnajua kwa kichwa offered. 1.96 squared is 3.84. What is what is 2 squared? 4. So you're missing what? 12 out of it. Like, I mean, there's a way I work things in my head. So it's 3.84. I'm missing 16 because of the square part of it. So we have 3.84. No, I just want us to work on it first. So we have 3.84 times 0.5 bracket 1 minus 0.5. That completes that. Divided by 0.05, right? It's 5%, so it's 5 over 100. 0.05 squared is what? Hiyo mmeshika, good. Run that code. Three? Where? At 368. How is it got 368? You're running 384, yeah. So that's typically what every student goes for. And unfortunately, most of the people who taught us, when they're sitting there judging our master's projects, they always ask, why you need to get 384? It is not a must you get 384. You have the reasons now, right? The prevalence can change. If the prevalence just change, if the prevalence on that particular equation, see the Chini, on that, okay, actually, see, I think I made a few, Chini. So let's say the prevalence is 20%. It means it's 0.2 times 0.8. Run that. 240? Okay. to me around our figures, 246 somewhere there, isn't it? So if the prevalence is 50%, the sample size goes to 384. If the prevalence is 20%, the sample size comes down to 246. Why? Why? What is the reasoning behind it? Yeah.
Okay, the proportion in the population with the disease are few compared to now the population having without the disease.
Say that again.
The population with the disease are few compared to now those which are free with the disease. So for that case, that small sample size or the required sample size to get that 20% is 346.
What is the difference between what you have said and saying the prevalence is low? What is the difference between what you have said and just saying the prevalence is low?
Low prevalence gives you lower sample size.
Why? We talked about some things yesterday. I want you to connect the classes. There's a reason why we structured these classes the way they are, and we are building on something. Why?
Lower prevalence means that the condition is much more rarer in the population.
That is the same sentence. Low prevalence means the disease is rare in that population. It's like saying that vehicle has a black tire. I mean, so I want you to give some kind of a theoretical reason. I've drawn something there that I think you're used to by now. I want you to leave this place not just taking formulas as they come, but trying to get a reason behind the formulas as they come.
For me, I'll not think like an epidemiologist.
Okay.
Nitafikiria kama statistician.
Yeah.
So if prevalence is A plus A plus C over N. Yes. And here you have said we are interested in conducting a cross-sectional study in a population yenye kona ugonjwa. So if the prevalence, if the people who are when you're kona ugonjwa wana reduce, if that prevalence is going down, and we're interested in the population that has the disease, then we're expecting the sample size to go down.
Okay, so what have you said? let me try and guide you a little bit. Yeah, give him the microphone.
I'm saying the target population becomes lower, so therefore you have a lower sample size.
The target population becomes lower. Okay, think about it this way. What is probability of disease positive? A plus C over N. So, now, I don't want to go into the probability part, but let's think about it this way. If this probability is going down, how can we approximate those who are diseased as an odds ratio? You remember the way we were doing a risk ratio? It was A over A plus B, right? When you're thinking about like in the exposed over the unexposed. So think about it that way. Then you realize that once we start having a lower number of A, that is those who have the disease, then we don't really need A over A plus B. We can approximate A over A plus B as A over B. That is where when you do an odds ratio, when the numbers are low in the cells, we actually not even, if you're going to do the risk and the exposure, it's just A over B as an approximation. Take some time and think about that in terms of how it influences how we think about the sample size when we work. Because then, if you're going to be approximating just as A over B, then you really don't need, because if you need a larger sample size, it's A over A plus B. But now we are approximating A over A plus B as A over B being equal to that as well. Take some time and think about that. I'll give you slides tomorrow. We'll cover that in detail a little bit tomorrow when I'm discussing diagnostic tests. So when the sample size, when the prevalence is 50, the sample size goes to 384. So, which is what almost everybody in KU, JKUAT, Nairobi, Maseno is always hammered to get to that number. But now you see you can justify it based on certain parameters. We always say assume 50%. But you know, assuming 50% is a very big assumption. If you think about it from an epidemiology perspective now, when you have a 50% of the disease, surely, you will see something different in the population. Most prevalences range between 10 and 20, and maybe if it's so high, maybe 30%. But then that depends on published literature, previous studies, and sometimes expert elicitation. So, what is an expert of that code? So what happens if you change the prevalence to 60%? Run that code. 368. So that is just kind of giving you kind of a range to play around with. So now, look at me for a second. So we have just factored in the prevalence, the 95% confidence interval, right? Those are just the two things we have looked at, because then that gives us the Z statistics, and that gives us the precision. Now, what other thing can influence the N? Leave that formula the way it is. What other thing can influence the N? The target population. What about it?
This formula does not take into consideration how big or how small the target population is.
Okay, so that's one side, eh? How big or how small the population is. We haven't covered this. Okay, let me ask the question and then so that I gauge where we are. So if you're going to sample from the target population, how can you sample from that population? If you have an N, don't worry about what N is. How are you going to sample from that population? What strategies can you use to sample? Randomization, that's one. Sorry? Stratified by? Age. Okay, what else? Cluster. So there's some kind of a design to how we are going to sample it, right? So we can think about a design effect. So we are together. We are moving one step to another step. So you can see the formulas. So let's remain with the formulas. You have the notes. You can open the notes in your side, just for you to see. I'll go through this a little bit just for you to get an understanding of what it means. Remember, this study was from the iron deficiency in women of reproductive age. So we have I messed up. There's a slide I've left out. In your code, enda chini kidogo. I think I started developing the code and then I realized I need to make slides jana usiku, and it was too late. It was like past midnight. If you go onto your slides, you see the formula down there. Let's start with that first. You see the formula where there's Z squared, PQ, multiplied by def, right? Divided by D squared. You can see it, Yes. Oh, line, yeah, so you can see that. So the def there is called the design effect. So I was making it in the R code, then I realized I needed to provide something for people to be able to refer to later. So the design effect comes from interclass correlation. If you're going to do like a cluster sampling, for instance, or whatever design you use, you're going to get some kind of a correlation between the classes. When I say a class, what do you understand by it? Or a cluster class, what do you understand by it? Statistics, AP, econometrics, we all use the same language, just different words. What is an intra-household difference when you go to sample in Masai Mara or sample in Siaya? The differences within and without the house. So, objects closer together from geography are similar to objects far away from each other. So, the same way, no, I'm defining, there's something I'm trying to define, kidogo. The same way, within a house, we expect those people to be more similar, so within a house, than between houses. So, when we collect samples and we have some kind of a clustering, what is clustering? Grouping. What is grouping? Similar characteristics. There's a reason I'm asking that question because if you're going to come to his house, for instance, and he has 2 kids, and you're collecting samples from both kids, and we have a repeat of that in multiple houses where we're collecting 2 samples from 2 kids, 2 kids, 2 kids, we're going to have clustering within individual households. So, and we need to factor that in when we are going to sample. So, that difference between the houses is known as intra-class correlation. That is the ICC. Now, the ICC, you have your note there, but it's a measure of homogeneity, which means similarity with respect to variable of interest. So, it can be households, can be individuals within a cluster. It is sometimes referred to the rate of homogeneity. Because units in the same cluster can be similar in one way in terms of things like income, climate, environment, attitudes, practices, and stuff like that, the ICC is almost always positive. The def can be described in terms of ICC, and I'm coming to the def down here. For a given def, so kwa your code, nime define def. Kwa the code, the sentence above it, I put a definition in there. So the design effect, it's called design effect. The design effect is an average number of units sampled per cluster, n bar. So the ICC can be estimated as the design effect minus 1, n bar minus 1. Now, if you read Apoju, there's a way in which you define the design effect. But upper chini, it gives us a way in which we can estimate design effect, which is from a second survey, we can actually do a calculation of how we multiply it based on that. So I wanted you to kind of think about it as the design effect, which is approximately 1 plus n bar minus 1 times the ICC. So if you can get from a published paper what is the interclass correlation, you're able to define that. Typically, it can be like 0.2, 0.3. I think, Moema, in your study, you used what? 5, yeah, 0.25. So that's his expected difference, correlation difference between the house. So you multiply that by the sample. Now, there's that formula up where there's the def. Just copy that formula and then go down. Never interfere so that at least you know you created whatever, something chini yake. Copy it, copy paste it under it. And then instead of the def, let's use Moema's 0.25. You've heard how the design effect comes in, the interclass correlation. That's what we're using. 2.5. The expected differences between the 2 households based on the variable of interest. So when you put in 0.25, and then use a prevalence of 50%. Chini kabisa, kuna mali imeandikwa def. Hiyo ni kitu kidogo bwana kwa R. 96. So you see the sample size is coming down, right? But remember, hello. Remember our confidence interval is 95%. So we are still maintaining the same confidence interval. You have done 0.5 times 0.5, right? Times the 0.25, So you can see the sample size comes down. So we are able to even reduce the sample size, but maintain the validity in the study, even with a smaller sample size, as long as we are able to justify what we're actually doing. So, now, let's go back this side. We've talked about the prevalence, right, of the disease in the population, or the prevalence of the outcome of interest in the population. Let's use appropriate terms. We've also talked about the confidence interval that we're using. Can be 95, can be 90, can be 80. And also we've talked about the design effect, which means what effect the design has on how we are going to interpret our N. Sawa. Now, you can play around with it when you change the design effect and see what is there. And look at your study. Look at your study and look at what is there. Sawa. What else? Yeah.
So what you're using, because you say now this is based on the fact that you've done clustering. So what if you've not clustered? Let's assume now it's totally you've not clustered, maybe you're just using whichever the sampling.
You will need a larger sample size. You'll need a, so you may go to 400.
Okay, so that you not use the depth.
No. No. You're only using the design effect to account for your design. And you need to kind of, before you put that number there, you need to kind of look at it. So if you're going to do like an RCT and you're doing a, you know, like you can do a one-stage cluster sampling. You can do a two-stage cluster sampling where maybe you identify certain villages, and then from the villages you identify households. And then you have to account for what does a two-stage cluster sampling kind of a design effect look like. One stage you're just identifying villages and randomly sampling through the villages. You know, that's another design effect that you need to look at. And when you go to the papers, you can look at their interclass correlation, the ICC they are doing. Safi. Yeah.
So if you adjust for clustering during the sample size calculation, would you also need to adjust for the effect during analysis?
No, because now you're going to analyze your sample, your data based on a very specific format. Here you're calculating a sample size. Hatujafika kwa analysis. We're going to come there. And I'll share a few things from his work and from some of the work we've done. We'll show you a little bit of some of the stuff we've done. Now, prevalence, confidence interval, right? Design effect. What else can change, can dictate how many samples you get, how many questionnaires you get from Siaya County, from Marsabit to Nyongnyong? You're going to do questionnaires. What? Yeah? Power of the study. What is power of the study? I would have done this is in R, but I thought maybe it's easy to explain to Kifanya, then, because it's a very short code, but I can make it long, but it has idea. I thought maybe just doing something so that you understand the sample size, then you can, the rest you can go study by day. What is power of a study? Kenya Power. Hold on to that. Okay, what is the power of a study from this? We're going to come back here. I told you the whole week we're going to do 2x2 tables back at Chokenai. The true positive. You sure? What is power of the study? Power is what? In formula. 1 minus beta. What is beta here? Hold on to that. What can change when you go to the field to do questionnaires? You're going to Kwakina Purity. You have identified 600 households, right? What can interfere with you getting 600 households? Let's use some basic, just basic thought. Some people might not what? Might not respond, right? So non-response. Those are things you're going to do you're going to get there. So response rate. So you need to, you can account for your response rate. Normally in some studies they'll tell you we recruited 600 people, but we got 520, right? You can calculate a percentage out of that, right? We got 500 out of 600. That is what percent? Hesabu kanaruka, eh? 5 over 6 times 100, which is basically 500 divided by 6. So that's coming to what? It's about 80. Now, so you can say you have a response rate of 80. So you need to account for that. So the reason why I brought this formula, because it's one of the most commonly used formulas and one of the most abused formulas. So if we are going to account for a couple of response rate issues, we have J, so we have the Z squared PQ design effect over, we don't have to include all of them, but J is expected response rate as a proportion, K is the average household size, L is basically the proportion of the total population accounted for by the population group of interest. We don't have to account for all of them. We don't have to account for all of them. All we need basically is to response rate. So you can just say J D squared. So in your formula hapo chini, in your formula, copy that formula down, the def one that you just wrote, copy it down. We maintain z squared as it is, so it's 50% prevalence. The def we're maintaining at 0.25. What response rate do you use? 80, okay, 80%. So that is 0.8. What sample size are you getting? So all you're doing is just 0.8 times 0.05 squared. So, sorry? What there? Oh, so we are doing another. So we first did a general calculation, right, without adjusting for the design or the response rate. So then the second one, where there was a def, we added the design effect. So now we are adding in response rate. The response rate comes down here as part of the error. So under the precision. So it's we're using 80%. So 0.8, just add 0.8 to the 0.05 squared. How do you add? Multiply. So before the 0.05, you can just put it outside the bracket, and then you put a star. So 0.8 star times the rest. What are we getting? 120. Huyu anapata 76, huyu anapata 120, huyu anapata 77. Hebu mwandike code aje.
Hii ya kwanza niliweka hizo. Into bracket. Without bracket you get a figure like 491.
Do this, eh? Hebu try this. Kuja hapa kwa star. Hapo. Weka bracket ya kufunga. Haya, kuja hapa nje. Weka bracket hapo. Weka bracket ya kufungua. Haya, weka bracket ya kufunga hapo. Yes.
Nishafunga.
Oh, sawa. Hebu piga hiyo.
Iko sawa, ndio inakuja 77.
Hebu run hiyo. I just want to see. Before I talk, I didn't run. Sawa. So, what numbers are you getting? At 0.0. No. So when you write it this way, what are you doing? What is the 0.25 doing? So you need to bracket this all first. Nakumbuka board mass. Alafu, kwa hii 0.05, make a bracket pia ifunge kando kivyake, square. Because right now it looks like you're multiplying this and this and then squaring. Yeah. So just, normally I try to write it explicitly. Mko fiti? 280.
You're replacing with 0.5 or...
See, the formula ndio ile pale. The J is on the precision side. It's divided by. So, inafaa kwa hii side. So you bracket this, multiply by 0.08.
So the...
So hii ni 1.96 squared times 0.5 times 0.5.
Okay. Oh yeah,
0.5
this is supposed to be 5, yeah.
times 0.25, which is the design effect.
Design
Sindio?
effect, yeah. So
Divided
hapa
by
ni
bracket mbili. Kuja hii side, bracket times 0.8, close the bracket. I run that. Wacha mchezo. Ilete kitu kasa hapa.
Okay.
What's your shortcut? Hii ni mark kama ni?
Hii ni...
Okay, so control enter. Here you're getting 120. Yep. So the number is? 0.000. Wacha hizo. So 1.96 squared times 0.5. 0.5 times 0.5 PQ, 1 minus Q, 0.5 times def is 0.5. The def we said is 0.25.
Yeah, that we have already put here.
Oh, okay. And then all these, yeah, that should be that way.
That's even smaller.
No, do I add a bracket here? Yep, should.
120.
Yeah. So Has everybody gotten 120? Aya, angalia hapa. We are using this particular formula, right? Sawa. Please watch, angalia pande hii. So, we said def is what? 0.25. Sawa. We said we are maintaining 50%, right? Sawa, sindio? And then here is where things are going crazy. 0.5. So here's where things are going crazy. You do that times 0.8. Put a bracket. Yeah? So we are doing 1.96 squared, right? That's the z square times p 0.5 times q 0.5 times design effect 0.25. All that we are dividing by 0.5 squared times 0.8. Safi? 96 kure. 96 wapi? Eka bracket. Angalia bracket. Look at this. This is where the challenge is coming. You're squaring this first before you multiply. So, we are good? See, at least now we are clear in terms of how you can design a cross-sectional study and how you can play around with the sample size based on different factors. Because somebody can ask you what's expected things and stuff. You can see very quickly that if you're, let's just play around with it. So, that is when the response rate is 80%, right? What happens if the response rate is very poor? Let's say, 10%. What will you expect? No, usifanye thought process. I want you to reason. I want you to reason. You already know at 80% there it is. Population, the sample size to increase, right? You expect it to increase. So change it to 10%, the response rate. 960. You can see how big of a difference that is. Where if you expect to go into a community and the response rate is very poor, and this is where I'll say, don't expect the response rate to be very high. Compare, because people never report how many people they recruited in the study and how many responded. But if you're very careful in terms of what they're doing the analysis, you're able to pick that out. It's very rare in certain communities, especially pastoral communities, to get a response rate of 80%. It's very rare. It's very rare. I covered over 15,000, 20,000 kilometers in Masai Mara, and I can tell you, between sampling questionnaires and samples and humans and stuff, it was messy. Some households will go in and I will cancel the questionnaire because I can tell they're not telling me the truth, and I know that's going to bias my study, so I'll mark it out and put it on the side. Some studies I'll go in and people will come, 4 of them, to answer one questionnaire, I'll put that on the side. So the 165 I handled were where I was introducing, like talking to him as a person or as the household head. So understanding the response rate, that's why I didn't want to dwell more on things like the income and all those kind of stuff, the characteristics in the family, because then you start shifting a lot of stuff. We do that especially in the economic side when guys are doing econometrics, but it's because they really want to get a precise measure for certain specific things. So if they're going to calculate like the socioeconomic status, SES, of a household, they want to kind of like, most of the time they build a composite where they look at, do you have a mabati house? Do you have a bicycle? How many chicken do you have? Do you have sofa sets? Do you have like a broom? Do you have, and they'll provide like, do all that, and then they provide like a composite index of what is SES. So you know that precise measurements gives them that. But that becomes a challenge sometimes. For those who are into social epidemiology, there's a very nice book by a guy called Michael Ox and Gleimer. Gleimer is a lady, super nice. Michael Ox was my former mentor, and basically some of the guys who made us go into this. He's a social epidemiologist, he's a methodologist. So basically, they do methodology. There's another guy called George Maldonado. You can go through some of his papers. They can be complex, but if you can spend some time, it takes like 3 or 4 reading per paper for some of us to get it. So it's kind of complex, but it gives a little bit of some of this sample size and stuff. Another good author is called Sandra Greenland. He doesn't publish normal papers. He has a site where he publishes because his papers are like 40 pages long. And they are super complicated, but they provide some background to this. Are we good with cross-sectional studies? And now we can think around. Sindio? The way you design cross-sectional studies is different from the way we design others. I'm not going to go through each study per se, but as we build through the whole week, I'll make sure that we do get to go through that. So, this is an example of the same thing we have done in the first. So this is a study that was being conducted on 6 to 59 months of age kids, vitamin A deficiency among kids 69 to 59 months of age, assuming that prevalence was 35%. That is the prevalence of deficiency. Please note, when you're doing nutritional studies, things shift. We were just working with one PhD student who we are just finishing right now with a couple of papers, and we had to sit down and redefine, when we talk about animal source foods, is how much did you eat in the last 24 hours? When you talk about folic acid deficiency, we're not asking how much you consume. We are doing the opposite. 2 by 2 table. Remember that. The prevalence is A, right? But then we are interested in 1 minus the prevalence in this particular circumstance. We invert it. So you need to really think through that a little bit. So this is basically just the same calculations. So in this one, you can see they did that, 1 minus that, times a design effect of what? 2.5. That's a high design effect. It's a very high design effect. But that's because of the complexity of measuring a vitamin A deficiency within it. So you need to really do a different sampling technique. Here, there's a design effect, and then they did the JKL, right? You remember the JKL in the previous slide? So he did all that plus the D squared. You remember it? By accounting for that, the sample moved to 3,254. By adding everything together, when they talk about decreasing the acceptable level of precision to 2%, so you can change your sample size by decreasing the level of precision, right? When you decrease the level of precision to 2%, it means your confidence interval is what? Is what? 98. Your confidence interval is 98. That is why your precision is coming down to 2. We normally use 95. That is how our precision comes to 5%. So, that is a very risky move. You cannot go to the field and be 98% confident. Even if you're going to do analysis, I would rather stick with the known 95%. But they were doing that because they wanted to kind of play around with that. So decreasing the acceptable level reduces the number of households visited by more than 1,500. Using an acceptable precision of 0.07, that is 7%, the results in the household sample of 1661. So they used 0.07, which is 7%. So they used 93, which is within, because you can use between 90, 80, 95. The design effect? Tulikuwa tumepitia hiyo. ICC, interclass correlation. Oh yeah. So, are we good up to there? Yeah. Yeah. I love that question. I know it's going. Yeah, there can be 10 studies in one area that are reporting different, let's say, design effects, so, or different prevalences.
And then number two, what of in an instance where such reports are lacking there? I mean, there's no reported prevalence, or maybe whoever's doing the study cannot find somewhere it's reported.
What is the prevalence of tick-borne diseases in Marsabit? You need to check. Let's say you go in the paper and you don't find it. Sorry?
You assume that it's 50%.
You assume it's 50%, but that is assumption, isn't it? What if you don't want to assume, or you want to make a better gaze? When we conduct a study, we have two types of, kidogo tu, senda hapo kwanza. We have two types of validity. We have internal validity and external validity. What is internal validity? Ate? In the local context, well, yes, within the study population. So, sindio? What about external validity? Generalization. I'm looking for that term. Generalization or extra. We normally talk about extrapolating your results to similar environments. So one way is you can look at a similar environment, and Garissa and Marsabit are not so different. If the studies done in Garissa, you can assume they can apply to Marsabit. Then there's something you said. Pilot testing. Typically, you don't have money to go pilot testing. So what can you do rather than go pilot testing? A cheaper way of pilot testing. Expert elicitation or opinion. So, all those are acceptable methods, and you can write that because we have citations for that. I don't want to go through the whole of this, but I'll walk you through this and then we move to the next thing. What is a cohort study? What is a cohort study? Speak up. You have the answer. Amani ugali meja bado. So what is a cohort study? We said outcome and exposure. Use those two. Thank you. Chapa shughuli, chapa shughuli. Chapa shughuli, chapa shughuli, chapa shughuli.
In a cohort study,
Eka microphone hapa.
in a cohort study, the outcomes is known.
Eh?
The outcome is known. Is you're dealing with the outcome.
Hey. Amemeza maneno hapo. Okay, who can give us a good try quickly? Songe. Ni bebe. We have been talking about this thing kwanzia jana. I don't want you to cram. I want you to understand it. She's saying something, but she's mixing two things. The kind of study you've described where the outcome is known, so you're selecting based on, the outcome is unknown, but the exposure is known. You need study again? No. Okay, so let me put it this way. Let me use a case control, so that I use a different one, then you can define cohort. So, in a case control, you're selecting from the population based on outcome, sawa. So you're selecting, you're recruiting based on your outcome, and then you're looking for their exposures. Use the same sentence, or describe cohort.
So you have individuals who do not have the outcome. You recruit them, you expose them, then you measure the outcome.
Thank you. You start with a population, and you want to make sure that population is disease negative. Disease negative. We are using notation here too. Notation. That's why the first slide I talked about notation. Disease negative, sawa. And then we give them exposures and no exposure, and then you look for whoever develops the outcome of interest. I would like you to kind of shift that a little bit, because it makes a big difference, where you are looking at a population that is disease negative or free, and then you're going to be giving them a set of exposures, and then measuring at the end whether they have the outcome of interest based on this set of exposures. That is why when you're looking at, remember the smoking example? Smoker and a non-smoker? And we can have, the smoking is one of the best data sets that you can use to teach anything. A lot of different stuff. So for cohort, we want, and these are just slides I'm giving you, and then I'll work on something maybe when nikikaa chini leo siku, working out on the tomorrow's code a little bit on shifting. So we need power. Wapi mtu wa power? Ndio hiyo hapa. Power is probability of detecting a real effect. Okay. I have them in tomorrow's slide. I didn't realize I needed to put them today. What kind of errors can you get in a 2x2 table? Yeah.
Type 1 and type 2 error.
Type 1 and type 2 error. What is type 1 error? In which column? In which cell? A. And type 2? Okay, let's start with that. Then we work out. So how does A become type 1 error? Think about a hypothesis. Sorry? Now, let's walk through it. I normally love when we discuss, because everybody is gaining through it. So, A is a true positive, so it becomes an error when it does what? Let me use that. Let me use this. So I can Google it, but let me try and use this kind of a thing. So we have 1 minute just on this, and then we can move in. So what is a hypothesis? We are deciding that. Right? So that's how. Normally we have a what and a what hypothesis. A null and an alternate. An alternate, right? When we are looking at the probability of rejecting a null or accepting the null and rejecting the alternate, what kind of mistakes can we make? Type 1 and type 2. I want us to discuss the words. You can reject what? You can reject the null hypothesis when actually you're not supposed to reject it. What is that? That is type 1 error. Okay. Tushikilia hapo. And then what is the other side of the story? You fail to reject when you're supposed to. What is that called? When a man has a kitambi and he goes to a hospital and is told he's pregnant, is that a type 1 or type 2 error? I'm giving a very practical example. Think about it. I'm using a very practical example, and I have a photo of that I use for teaching. If a man has a bigger stomach and he walks into a hospital and he's told, congratulations, you are pregnant, is that a type 1 or a type 2 error? Think about it, Vizuri. The reason I'm using that example is because I'm forcing you to think a little bit in terms of what is your definition. And the same 2x2 table. The same 2x2 table. What have you done wrong by telling the man congratulations, he's pregnant? False? So that's a type 1 or a type 2 error. Now, are we clear? So you can work the rest on what's a type 2 and where it comes from. Where is the false positive here? So that's a type 1 error. That's why I'm using that example. When a pregnant female, let me use that term, walks into a hospital and they're told you're not pregnant. That is a false negative. So that's a type 2 error. Please take some time and understand that. Remember the pregnancy example. It's a very good example for teaching. The man is not pregnant. You falsely told him you're pregnant. So it's a false positive. It's a type 1 error. Then you can now read the rest and then now build your knowledge on that. Are we clear? So, Okay. But hizo ni slides za kesho. Hizo si za leo. I just thought I'd clear that out. So there's power. I'll just go through this quickly, and then you guys can walk through the code for some other thing up to a point, and then we'll continue that code until Friday. So one code, we will talk with him kidogo. There's another code I want to kind of modify a little bit from his side, because I think you guys might gain from it. There's one I wrote in the morning when I realized some people are struggling defining a few things. Then, yeah, but some of them I'll just give you. You can go home and then work through them. As long as I tell you what it does, you can go and look at it. So, power, cohort study, sample size, sawa. We are done with cross-sectional studies, so sawa. We are comfortable now, studio. For cohort studies, I think Thumbi discussed it very nicely. Janet discussed it very nicely. Nkoranga discussed it very nicely. Here, we have power, which is the probability of detecting a real effect. In this cell, which is the beta? Because power is 1 minus beta. We have alpha, the probability of detecting a false effect. Wachana na history ya two-sided kwanza. Alpha, the probability of detecting a false effect. Everything in epidemiology starts and ends in a 2-by-2 table. Everything, everything. That's why I told you, spend some time on this, even if it's a whole week, and understand an exposure, a test, and an outcome. It will really change how you think about epi. It's one of the sweetest things that once you learn, becomes very interesting. PO is the probability of events in the controls. P0, sorry. P1 is the probability of event in the experimental subject, right? RR, relative risk of events between experimental subjects and control. M is the number of control subjects in the experimental subject. I'll delve through this later as I move, just so that we don't have to spend a whole time. Partly it's because there's one slide I was supposed to have at the end that had a formula. Oh, ndio. Let's go through this quickly. Practical issues, you have power, can be 80, 85, 90. Try several in order to explore the scope. 5% is the usual choice of alpha. You can see where it's coming from, isn't it? It's 5% because it's coming from a 95%, right? So it will change if you change some stuff. You can keep it constant, but you know you'll be making an error sometimes. P0 can be estimated as the population prevalence of the event under investigation. If possible, choose a range of relative risks that you have the statistical power to detect. So, the formula, which you're not going to work on right now, looks like that. That's the formula. I've attached a link on the slide when I share. We have them actually. So, this is the main formula. So, this. But you have P bar or bar 1 minus, which is basically same as Q, right? But has a different calculation. P1 plus MPO, M plus 1. And then you have a couple of things. A difference, right? Experimental group controls, experimental groups squared. So when you spend some time, look through this, learn to write this in R. Those brackets are very important. Those brackets are very, very important. And then remember there's a square root. There's a square root. And the lower one has a square after being divided. You can define this. One way of doing this is always, you can define this first. So you define P bar, uko juu, do a small calculation, have it. So do an NC, have it, then just, instead of putting the numbers, you just leave the letters notations in there, because then you've already worked out the small sections by themselves. Like what is M? You can assign M is equals to this. So 1 minus M is equals to this and that. We are good? This is called epitools. It's a very interesting thing where you plug in numbers. I normally don't encourage any participant or any student to learn to plug numbers. That is why I don't like people using stata. I like you thinking about what is happening. I like coding because it helps you think about what are you doing. You saw the small formula about design effect divided by j times d squared had some issues. It's a very small equation, but you can see how defining where the brackets go into, and that means you're thinking what's happening. When you're writing that, you're basically thinking of body mass, right? Which one is being solved first, which one is being solved second. So I would encourage you to go in there, but at the same time, because now you are proficient in R, when you click that side, you write this formula and then see whether it gives you the same. So you do the formula first in R, get your number, and then go and see whether it gives you the same. If it doesn't give you the same, before you think something is wrong, can you read on what are the conditions that are there? Because you might be putting in a different P bar. So always don't start with what is wrong. Start with what could have entered differently. So I open the second code. So we have covered the cohort on that. As I work through the other codes tonight, I might add in like some kind of a thing for maybe RCTs and stuff. And then we just kind of figure out the rest. The rest I think you may have to learn by yourself. But the way we design case control studies is very similar to how we think about cohort, but then we're thinking of the opposite side with just a slight difference. The other, hiyo coding ile kwenda nini? Neto nini? Cross-sectional. Is it cross-sectional really? Day 2. Cross-sectional. Don't open the logistic. Cross-sectional one. Wewe wachana lines. Wewe fungua code. Now, over the next 3 minutes, over the next 5 minutes, because you're going to use this for quite a long time, how many have tidyverse installed? Please, focus kidogo pandei. How many have the packages tidyverse installed? How many have the package tidyverse installed? Okay, how many do not have? 1 minus P. How many don't? Hila, nani? Ngetich, angalia nyuma. Joy, mtanisaidia kwenye waja install. Please, if you haven't raised your hand, I want us to work together. If you don't have tidyverse, raise your hand. As you are working with those people, hello, kidogo tu. Please look at that code. There's a series of packages there. Please make sure all of them are installed in your computer. That is for everyone. So we are going to be working on this code until Friday. So we're not finishing. Today we're just introducing it, and then we move. Make sure we load kila kitu. Zote ziende, tidyverse, easy zote. Install zote. Janitor, no labda zini nini tu. At the start of the code, there's a series of packages. Make sure each of those packages is installed in your computer. We'll figure out the rest. The line of code is install.packages, quote, take the name of, kuna tidyverse, kuna hizo zingine, kuna janitor, kuna package. There's a couple. Umezipata? Baka sana. Kwa nafikiri kila mtu ni wa Manchester kama wewe. Which team do you support? Expert gazing over prevalence. Niaje. Sasa nataka una install tukisonga. You do install, it will bring you .packages. Then normally you put quotation. Tidy. You have tidyverse?
Yes.
Already have it?
I hope so.
cause nimesha need the
Yes. See, inafaa kuwa inaleta nini tu. Let me just continue with it. Let me just see. There's no package called Tidyverse. Buddha. Wana tuenjoy jamaa. Ikimaliza, you go to the next. Arsenal, officer, deployer, janitor, parkman. Please make sure the janitor, the parkman, the arsenal, which is different from what from Manchester, and the rest as you move, ziko zote installed. Yeah. Package.
It automatically detects if you have the packages and automatically does it. But it's such a long process.
Eka tu library maliza. You want? Make sure all this you have installed. Tidyverse, Arsenal, Officer, Nutrition, Deployer, Janitor, Parkman. Kuna hii read Excel. Though I think nili convert your data into nini. I think nileka CSV. Yeah, nileka CSV. So, but anyway, the read Excel wanzaacha tu. Because I thought the initial data ilikuwa Excel. Nikai change because I realized itasumbua watu wengine kidogo. But you need to learn how to load data, which is either Excel, which is CSV, can be text file. Sawa. At the same time, you also need to learn how to set a working directory. Because sometimes you may have 6 pieces of data in different Excel, so you just want to work from one folder, combine and save them from there, so you can, at some point, ukiwa nyumbani, learn how to set directory. Set a working directory, and then now you can load them differently. You can just say A is equals to dot this and that. And that is sometimes when you're working on multiple data. E-dataset, this is clean dataset, but it came in 5 Excel sheets, different Excel sheets, where we had to join like 7 stuff. Umeinstall zote? Zote, mpaka janitor parkman nini? Ah, good, safi. Alright, so then activate hizo basi. Uko fiti? Zote ziko? Janitor, officer, Arsenal? Haya, songa nazo. Are you done? Are you done? Hey, are we together now? Are we on the same page? Hey, mamua mungi. Madam Molecular, uko sawa? Ah, okay. Leo uinu mkono. Nini yo? Sorry, nini yo? Run, click kuja hapa tena kwa hiyo Pacman. Run tena. Simeshi hapa.
Attaching package janitor. Following objects are masked from package tabs.
Hiyo ni sawa tu. Tutasort. Kifika hapo, there's ways in which you can suspend one package and work on the next. Ama rerun a certain package to make. Okay, are we good up to there? Yeah. Wait, tulisema 5 minutes bwana. We want to do 15 minutes and then we can do the rest of the stuff. Okay, who has not finished? Who has not finished? Wait, kwani tuko maandamano? Who has not finished? Okay, so this data set came from the work that is done by the Animal Health Innovation Lab, the project that is still ongoing anyway, but this is published data that a student called Hilary Wahungu was working on. Me, Mwema, Thumbi, Mutono, and a few others are part of this. It's a data set I worked on. It looked at consumption of animal source foods, so how many different groups of animal source foods you consumed, and also there's an extra data set from another paper with things like folic acid and stuff. So it is a very big data set. So we start with running, so the H1 basically pulls in that data. Pull it in. Load it. Load the data. Eh? Atake? Eh. Data si niliwatumia. Iko kwa hiyo folder. How do you pull in, how do you bring in that data to your thing? So go to that data. Please listen for a minute. The easier thing to do. Go to that data, copy the path. Copy the path. Sawa. You copy the path. Go back to where this go back to this line of code, erase the whole of it, apart from, erase the whole of this line, and paste it there. Copy the path of that cleaned data. You see the thing is called cleaned underscore data1.csv, right? Go to the folder that umetumiwa, copy the path, come and toa hii yote, apart from the brackets, paste it there. Ni copy paste, like nika kuvaa slippers ya left, alafu ya right. Like copy paste. The data kwa email ulitumiwa. The email that Moema sent. Kwani hiyo code ya kwanza ulitoa wapi? Cleaned underscore data1.
There was something you were doing, Ghana. Like a fix.
Code. Soft trap, long lines. Hiyo.
Thank you.
Wewe rudi juu.
Ndio hiyo.
Path iko wapi? Yeah. Kuna bracket na miss. Supposed to have a bracket after clean read.csv. Na huko. Sawa. Jaribu kurun, because I know what's going to happen. Sawa, imekataa, si ndio? Good. Yeah. I'm sure. Hello. Has everybody copied the path? Okay, can we be interactive, please? Can we be interactive? Because now it's like I'm not communicating with anyone, and we're just kind of moving around. Can we be interactive a little bit, so that we go step by step? You have a question? Do you need? Do you need to? It needs to be in your desktop somewhere, or in your folder somewhere. Okay, has everybody copied the path? Okay, can you run that code? No, just you're loading the data, the H1. Did it run successfully? Aye. 1 minus P. Who has not had his code running? You, okay. Yeah? Yes, so those who use PCs, give me a second, please. Let me just explain this. Hello, give me a second, everybody, just give me a second. Those who use PCs mainly, like the Windows, when you copy the path, most of the time you will see this. You will see C and then that, right? Sawa, a /. Please always change that to This is a backslash, a forward slash. Sawa. This is something very different between those who use marks. The mark copies the path as it is. For PCs, change this to that. So you want to have them this way. Yeah. Each. Kwa kila moja. Uh-huh. Ta. Uh-huh. Yeah. Niaje? Kamenuka? Kwa nini imefanyika? Now, next time, where's your code? This one? No. Code yako iko juu kabisa. Create spaces between your things. Okay. Now, what's the issue? Yeah, because you have not copied the code. Hakuna data. You carried the wrong thing. Copy the path. Path.
This is the path, yes?
I'm not a mark guy, but when you come on this, so the path is supposed to have this name, clean underscore data 1.csv. So come back to your R. So hapa ndani ya hiyo haya slash clean underscore data 1. No. Small letters. Clean underscore data 1 dot CSV. It has to be complete .csv because that's the complete path. I ran that. Safi?
I'm trying to get copy as path, but it's not that provision.
Iko bwana, ngoja.
It is not there.
Iko hizi kosa. Open with data. Send to copy.
Because I've
Properties.
opened properties.
So properties.
If you come to details, it is
Yeah.
there, but
So
it can't copy.
you copy that. Copy that. No, just highlight up to C.
Sorry.
C. Aya, copy.
There's no option.
Yako inakujaje? This is interesting. Ndio hii hapa. Yako is weird kidogo. Because it's supposed to have a
We've
path.
been struggling with the bit of that. Path is not coming.
So sorry. There you go. Are we good?
Are we supposed to run H1.2?
No. Just H. Not this one. No. H1.
Yeah, I've done that one.
Oh, okay. So that's only that. The one that's one. Come to code. Soft wrap. Long. Yeah. It allows the code, all of it to just fit. Yeah. Niaje.
Nimejaribu copy direct nikata.
Yeah, ita download hivyo. Data yako ndio hapa. Cross sectional. Clean data underscore. Right click. Where is the file location?
No, you've not clicked it.
Oh. Okay, sioni. Where is it? Oh, E. So, yako ni kama ule mwingine tu. So what you do with this, you where is the open file location?
You open or open with?
Hizo itakufungua. So you can just come onto this, you do that. So, Control C. Okay, first of all, code ukifungua mpya siku ingine, come here to code, hapa, click on that, soft wrap long lines. Your code fits onto the screen. If you move this side, you don't need a very wide thing like that. Now, so we take, because we know the name is right, so all we need to do is change that. Sindio? Yeah. Now, it copies ikiwa na hivyo. So all you do is change. 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 Yeah, you should be good. Run that. No. Okay, run. Good. So, tuko poa sasa. Aya, see, we are good. So, how many observations does that data have? How many variables? 866 variables. So, can you on your thing click view? Hello, let's work together as a group kidogo. Ndio twende haraka. Click view H1. You can type it here or you can click here. There's many ways to cook chapati, including on mkebe ya kimbo. Are we good? Yes. Imefungua? What is the first column? First column is what? Farming system. Then there's what? Household ID. Then you have the child ID. Then you have like the mother occupation and the rest. So, hello? Please follow me hapa kidogo. I want you to check out how many different types of mother occupation do we have. What I'm doing here is I had a small data set that we used initially, the birth weight, but I thought giving you messy data and walking you through how we play around with it to a point where we can analyze makes more sense, because I know some of you are already working on some data, or some of you are going to get data. Now, this is one way in which we're basically going to operate different packages and stuff, but at the end of the day, you get to see what happens. So, how many different types of mother occupations do we have? How do you get to that? Just one word. You do? You do? You do table. You do table, bracket, H1 and mother occupation. You don't have to complicate your life. Like, if you're told to walk from here to look for the most straight line. Unless you love sweating, which I doubt. So table, H1 and mother occupation. How many are there? Mother occupation is mother, OCCPTN. One way of writing words is removing the vowels. Si mnajua vowels? A, E, O, U. Too much? How many of them? So here they are. So let's work together as we move. There's a reason I'm doing this initially. I wanted us today just to introduce us to the data, go to a point where you can practice usiku. I also need to get home and refinish this code. So we have like crop production. We have livestock marketing. Hello, hello. Focus, focus, focus. We have salaried workers. We have fishing. Can you press, hello? Can you press the up bar? Up bar. what happens? The code comes back, right? So we want to know how many of these were in which production system. So what do? How were these distributed in the different production systems? There's two ways. Kabla uandike, think. I always tell you, think what the code is going to do. You have done table, mother occupation, right? Now, if you do, can you do comma inside that code, after mother occupation, comma, H1 and farming, see crop, where. Farming underscore systems. And to point out something. So, you have done that, H1 and farming system. See, ni kufinya tu enter. You don't have to click the whole word. Aya, imekujaje? You finger up, the code comes back, You finger up bar. Ile arrow. Naona pale inakuwa na arrow ine on the right side of the keyboard. Sikuna arrow ine. Finger juu code irudi. Then unaweka comma H1 and farming systems. This is how it comes. So, it gives you the different types and gives you the other one on this other side. I want you to take the same code, but now change so that the farming system is first. And then the mother occupation is second. Like farming system, comma, H1 and occupation. Meran. Comma, H1, ai ebweka ila nani kushikane, iko na space hapo. It can work, but nataka tu ikuwe complete. H1 and
So here,
yeah, H1 and farming system. Yeah, farming system. Yeah, kwanza. Farming. And. Umetoa and. Umetoa and. No, and sini hii. Dollar sign. Farming system ndio hii. Enter. Umeenda chini. Run that. Now copy, alafu change farming system ikiwa kwanza, mother occupation ikiwa second. So what are you seeing? Does it look more presentable or less presentable? So you prefer this one to the other one? So what do you prefer? There's the first one and there's the second one. The first one basically gives you a breakdown of the system types and then the numbers. The second one gives you each. If you're going to present a table on some kind of a paper, which one will you prefer to put? The first one. So it's always good to think about like how are you going to present your data. So, and the reason I say it's important is because you remember yesterday when we were doing, I think, the birth weight and all this kind of stuff, the weight was coming in differently. And remember when we were drawing the 2x2 tables, how you can shift things around? That is one way of doing it. Now, while we are still there, so let's assume your only interest was kidogo. So let's assume your interest was to take the first table and make it into a data frame. Umesikia comment yangu? Let's assume your interest is to take the first table because we just want to analyze something. So you can use that table for teaching. That's how we create data for teaching. We basically look for a small data set that we can explain, and then now we explode the data set. So let's say our interest here is going to be agropastoral as this as the outcome, and we're going to use this as some other stuff. So we want to make this data into a data frame. What do you do? Data? Say. Data.frame. So andika kwa yako. Ama kuja type kwa hii. Ama you want to say, aya, sema ni type. Data dot frame, hivyo. Alafu niweke wapi? Alafu? Please follow what just watch here, because there's something I'm trying to do, because it will allow you to do some stuff. Alafu? Hivyo. And then? Yeah. So what do you want me to change? Please reason with her. There's a reason why I'm making you go through this exercise. Reason with her. So, nieke, ya kwanza ikue? Okay. Aya,
why not do high farming systems or high mother of question?
No, this is a data frame. Hey, I love Bilona Hepanga question. Okay, aya. Data frame, alafu? Yeah, nisha change. Rada? Run. Say I've run it. Ndio hii. So, twende aje next? Aya, ndio hiyo code. Aya, object na kwa aje? So we call it what? Her data, purity. Purity 1. That way. Okay, so now we have purity that has how many observations? 88 and 2 variables, right? What are the 2 variables? Occupation and? Exactly. So it looks like that. So you can create subsets of your data and save. How do you save this in the folder where you took the thing from? You want to save it as a CSV, right? Sindio? Remember there's that code you were using where you picked out you remember this code, the H1 line, where you picked it from. So just watch a little bit. So you can do write.csv bracket, but now when you're doing write.csv, let me just explain it, and then we move to the next thing. So you do write.csv. The first thing you put there is the name of the data set. Sawa? It's called what? Purity 1. Sawa? Comma. You copy this path, but without the name of without that cleaned dot underscore data. Sawa? So we will copy that, but then change the name of the data set to purity 1.csv. Sawa? If you want to save it as an Excel data set, you can do dot something something. You can save it as anything you want. But as .excel, you need to write it specifically. Sawa? Ini CSV. Sawa? When you do it that way, it goes, the path, the whole path is that folder you created, so, until the name of the Excel sheet is what will change to purity 1. So you can always subset. So sometimes, are we clear back there? We are good? Aya. Now, will delete nini? Part gani? Will delete? So will replace na yako? Yeah. So when I do it, I'm doing it on my computer. You do it on your computer. Aya, are we good up there? What I've just said is what we are going to do next. You loaded the packages, sindio? Sawa. Aya. Now, please focus. Because we are going to do AP, but at the same time we are playing with the R. Because there's no way I can make you do AP if you cannot run the code. Sawa. We have 888 observations and 866 variables. Sawa. Which means there's sex, there's age, 866 of them. Sawa. We want to take what we need. So when you go to Mwema, he will tell you to create a questionnaire of the questions you want to go and ask in the field. So, please listen for a minute. He will ask you to create a questionnaire for your study. So, all of you, let's say you're working under SEMA. So, there's a project going on. One person is working on TB, the other person is working on measles, the other one is working on nutrition and everything. We will not conduct 50 questionnaire administrations in every household. We will make a tool. Sasawa. I want you to follow what you're saying. We will make a tool. That tool will have a provision for each and every person to ask their set of questions relevant to their area of study, so that you're not overlapping questions. Now, when you give Mwema those 866 variables, he will enter them into a tool. Sawa. What is an example of a tool that you can use for questionnaire administration in the field? Red cap, ingine? Survey? Sikuski? Survey still, Yaps, Kobo, So those are examples of tools we can use to upload our questionnaire. And then when we go in, normally we provide it with some specifics. So there's a household name, right? There's a household ID, for instance. There's a child ID. There's a GPS. So, I've used one example of GPS to, so when I write for you a code, I expect that when you find a similar problem, you can remember the code. So, it doesn't have to be the exact similar. If it's a matter of splitting one column into 3 different columns, for instance, you can do that. The way the GPS comes, it downloads the nothing and the GPS has a nothing and a I'm trying to make sure you're awake. A GPS has a globe. A globe is like this, sindio? Ukijo line katikati hivi, that line is called what? Line kuanzia juu mpaka chini. That is called a longitude. And then there's a what? Latitude. So a nothing is a longitude or a latitude? Hey. So when Mwema sends you that data has a easting and a northing. So easting is what? Is it a longitude or a latitude? Okay, we are in Nairobi, Kenya. Sindio? Is the latitude minus or plus? We have an equator in Kenya. We have an equator in Kenya. So are we minus or plus? It's minus. And those are things called data validity. You check the validity of the data you've been given. So, if it comes out as positive, you have to convert it into minus. Those are small things you check. So, the other things you check in the data is male can be capital M. Sindio? What if it's small m? When you do a count table, it will count the small m as a different variable. So you need to harmonize your naming system or kind of your variables. A 0, 1, you need to make sure it's 0, 1. Sometimes when people are so tired and they're interfering with the Excel sheet, akenda kulala at type 0.1. Now you come and you're seeing a 0.1. There's nothing like 0.1 because your categorization was 0, 1. The other thing I'll tell you is dates. Dates in Excels and CSVs are notorious. Are notorious. Spend some time and figure out how you want to enter your date. Whether it's 12 dot something. I tend to split them into different months and use clear thing, 2024, June, 01. To me, it works. I'll better gather them later on to do whatever I want. There's nothing I'm going to analyze based on the date. I can always combine two columns together. Depends on you how you do it. Now, we want to subset data for Vincent for his project. Sawa. His project is on animal source foods out of the 866 variables, not observations. Variables are this way, observations are rows. Sawa. We want to subset based on the columns. Please take note. Geoffrey utanisaidia hapa because najua kuna kwa mchanganyiko kingine maalum hapa. Nenda kukaa msahi tu. We want to subset based on columns. So in other words, one column is George, the other column is Vincent, the other column is Mwema, the other column is Geoffrey. Sawa. So you want to select these names. Sawa. Number one, you can select them by names. So sawa. If you know they live in columns 12 to 14, remember yesterday's code? Tulisema nini? In that 12 to, those are two ways we can subset. Sindio? What if it's a row? What if I want to select row number 17? Go think about that, because it will come in handy when you're trying to work on different data sets. So, because sometimes if somebody tells you that the first 10, 15 entries, not when you pretest your questionnaires, sometimes you discard some, but you have entered the data. So is this pentamix? Anyway, so you want to eliminate, you want to exclude the first 15, and then work on the other. 866 minus 15 is what? 8888 minus 15 is 870. So for this particular code, we are using a very simple line of code, very simple, where what we are doing is and you'll realize I tend to use the hash to separate lines of things just for teaching. I do it even when I do my own analysis, because sometimes your eye is so tired that you don't know where you are. And it happens because you're working at 10 p.m. and everybody at 10 p.m. is tired. So what we are doing is we are creating another data set called H1.1, and then we are subsetting. So I told you code U is like you're walking on a staircase or mahali kuna matope, sawa? So you are subsetting which data set? So you use that kwanza, and then you are selecting, sawa? What is C bracket called? It's called? Containing columns. I want the name, the R name. What when you do C bracket something? Conca? Okay. Yeah, that's the term. So we then have each of those comma as we move. Can you run this? We are going to work on this code until Friday. We decided we are going to go slow by slow so that all of us understand what you're doing. We are good? So H1.1 contains how many observations? 888. And how many variables? 29 imetoka wapi? 39, see 29. So you can see we have reduced our variables, so we've maintained the rows, sawa? So we have everybody in the study, but we have selected only the columns that we are interested in. Can you do table H1.1 and GPS coordinates? What do you get? You're done? Mnafaa kwanza kwa chap kidogo sasa. Table H1.1. H1.1, the data set we just created. H1.1, and we have 10 minutes, then we go. GPS coordinate. GPS, okay, GPS, it'll finya enter. It's the only one. Finya enter. And then finya enter ingine. Tuko sawa? How does it look like? Compared to when you did, let's say, mother occupation, where you had very specific categories. Now, click on that H1.1 dataset and go and look at how the GPS coordinates look like. Ndio hii hapa, kama unataka kuclick. So you can see we have, please focus for a second, kidogo tu. The data was collected in Masai Mara, sawa. We have a rough idea what coordinates we have, sawa. So we have minus 1 point that, then there's a space, sawa. Please watch here. There's a space, 35.88, space, 1892, that space 3.28. What do you think these are? What is minus 1.2? This is altitude, this is accuracy. It comes that way. When you get GPS data, it comes with longitude, latitude, elevation or altitude, and then accuracy. So, some data sets, so this data set is separated by what? Space. Space. Some are separated by comma. So, you need to see the data set so that when you're writing the code, if the separation is a comma or just a space, you use that. Now, go back to that code. Hii ni ya kufurahisha. Itafika mahali penye sasa tutaanza kucheza game. Aya, please look at this code first. Look at the code here, here. So, we are creating a new data set of the all, sawa. But we are using a pipe. This is called a pipe. It can be bar, arrow, or it can be what? Percent? Greater than percent. So, you can use either. So, now, what are we doing? We are separating in, so we are creating a new data set called H1.2, which we are deriving from H1.1, and we are separating the GPS coordinate. We bind, concatenate. We are separating, so we getting the first column, because there were 4, sindio? There was the minus, the 35, the elevation, and then the accuracy. So the first one will be labeled latitude, second one longitude, third one altitude, accuracy. And then we tell it the separation is by, so it's apostrophe, space, apostrophe. If there was a comma, we will do what? Apostrophe, comma. If it was a dot, we will do dot. If it was a bar or a slash bar or a forward slash bar, so anything that we use to separate, we will do that. You can also do this in Excel. I'm using it here just to show you how you can separate different stuff, and this is a code you can use to separate anything. If there are two things in together that you want to separate, you can use that. Sometimes, it can be, okay, let's say you want to download your papers from Google Scholar. So let's say you have 10 papers. You want to download your papers. Rather than going typing one by one of the best ways to do is play with the code. Play with the code. Go on Google Scholar, click on your profile when you're signed in. Go and click on your profile, go save all your papers. So, when you save all your papers, download them as a CSV. So, they will come with the year in bracket. So, you want to separate the year into its own column. So, that is the same process you're doing here, but now it's in bracket. So, you have to figure out, quote, bracket ya kwanza, quote, bracket ya pili. When it comes into the bracket, then what do? You rearrange by year. So, then now you have to bring back again so that the bracket comes back. I play a lot with that sometimes. So, run this code. So H1.1 had 800 observations and 39. Sorry? Error. Could not find? You loaded all the...
I think I loaded on. Should I load them again?
Just one second. Let me just see. Yeah, that's what I'm wondering. When I pick
The spelling.
spelling, that spelling is wrong. Separate is S-E-P-A. Sepa, sepa, sepa. Sepa, 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 sepa. Huh? See,
I'm saying even with that spelling
Yeah.
that you're saying,
like a library tidy. Tidy package.
it's there.
Is there? Umeload?
I already have it.
Vunja zote. Hata kuna zingine kwa kabati, chukua uvunje. Is a what? Small c. Ebu, make sure we load tidy package. Up on the separate iko. Make sure you have the tidy package, tidy R package. Make sure you do the, if at all it's not running for you, do library tidy R. Just come, actually. Enter library. Wewe andika bwana, type, wacha story mingi. Library, enter. Tidy, T-I-D-I-D-Y-R. Can you run that? Okay. Go back to that code. Do you run this? Can you click code, soft wrap, long lines? Code yako inafit page moja. Run. So the tidy package is where separate is. Okay, are we cool now? So at least now we know how we can separate two things. Sindio? Separate multiple stuff. So we've subset the data. Hello. We have subset the data. We have taken the variables we want. Sawa. Those are the variables we are going to do the analysis on between today and Friday as we work through the different stuff. Sawa. We've used a simple example of how you use a pipe. Sawa. How you select and how you do a separate. So sawa. Now, we want to record a few. So there are certain variables where we have them in a continuous format. Sawa. And we want to be able to categorize them into something. So let's say you have milk quantity, where a household had one meal, some had 2 meals, some had 0.8 and stuff. You can try and create categories. In creating the categories, you are basically trying to be able to, sometimes you may lose information, but for now, let's discuss how we kind of do the category. Yesterday, we talked about greater than 23. You remember that? That conversation, we said, when you say greater than 23, that means what? That means 24 and? Okay, if we say greater than 5 and less than 10, greater than 5 and less than 10, 6 to 9. If we say greater than or equal to 5 and less than 10. So remember that when you're writing some of these things. This is where we have problems where we start having things what do you call it? Overlapping. So that, because you really, when you come going to do an analysis, let's say for instance a regression, you want the categories to be specific. A male is a male, a female is a female. So we can argue about isomatrans zingine baadaye, but here hapa ni hapa. So if it's a category of low milk versus high producer of milk, the categories don't overlap. So because then we are not having a clear separation. So go to the code ya chini. We have a variable known as score, I'll share with you the paper that we wrote so that when you start working on it, but I want to kind of work with you in this, and then we are going to work on this data as we finish. So we have a knowledge score, which is a composite variable, which means it was taken from a set of variables that then we developed a knowledge score, we developed a practice score, and we developed attitude score. These are used in animal source food consumption when we are looking at how they relate. So please watch here kidogo so that we kind of work together, step by step, tukisonga tumalizie up, and then we can continue tomorrow. So we have knowledge score as a variable, sawa. We are using H1.2, so sawa. Typically, I would not use the data set I've worked on. I would say H1.3 is equal to H1.2, sawa. And then I work on the other one, but for now we can just work on it because we can always go back. So we are calling knowledge score, sawa. And we are recording it as anything less than or equal to 5, sawa. We are calling it poor, so sawa. And then we add an if else because we have multiple categories, sawa. And this is where it gets confusing. Anything greater than 5, less than equal to 5, sawa. So it's up to 5, so sawa. Greater than 5 is what? 6 and above, sawa. Remember this additional. Unlike other programs where you may say greater than 5 and less than 7, here you have to state H1 and knowledge, H1, 2 and knowledge, greater than 5 and less than or equal to 7. So we are taking 6. So we took 5 here. So here we're taking 6 and 7. We call it, and then we say anything greater than, so starting from 8 to, we call it good. Otherwise, NA. So it's like an empty cell, so with an NA. How did you get the 5, the 7, and yeah, the 5, the greater than 5, the less than 5, 5 to 7, more than 7? How did you get that? It's a code, but I told you, ask yourself what is the code doing and how did he get those figures? So we want to take a height of all of us, sawa. We will end up with a continuous measure, sindio? Not a binary, it will not be yes, no. It's a continuous measure, sindio? Now, how do we know when to say this is short, this is tall? What can we use? Unaenda complicate maisha. Make it simple. You can use the median. What is a median? What is a median? The value at the center of? What about a mean? Average. Now we are differentiating. So the median is the middlemost person, the middlemost height. So we can use a median. Why would you use a median, not a mean, in a height? Yep. So extreme or outliers. So we might have a long person. I'm not using tall. I'm using long. Like that guy, I don't know it's called, the tall guy who was moving around in vehicles, Gen Z, whatever guy. Now, him, if he is, let's say, 6'9", and our average height maybe is 5'10", you will realize that we will end up with we will be skewed to the right because there's an outlier. Sawa. That is called a right skew. We can also have a left skew. So we would prefer, in terms of this, to take a median. In terms of the milk, we would potentially look at the interquartile range, and we use that as definition for what is low, blah, blah, blah. So we can also take an average in certain circumstances. So the mean will work, depending on what we are looking at. So run that code. For everything you change in your data set, you have to check it to see whether it did what you wanted it to do. If you cook ugali and you end up with chapati, you know you're doing well. You have clicked the table. You do run that and then check. We are good? So what are you finding now? Fair are how many? Good? Poor? Now, look up kidogo. We are not finishing the code. We are just working slowly and then the rest will run. Now, if you have a data set that is, let's say, good and bad. Okay, let me use that. What will be a reference category there? Assuming you're not Christian. Okay, so that's a poor example. Let me use short and tall. What will be a reference there? Technically, you'll use short. Sawa. Sawa. Now, if it's N, no, and yes, in R it works okay because it takes the first alphabet. Sawa. What it's doing here, it has taken it alphabetically. Sawa. Fair, good, poor. What will be our reference here? Poor, right? So that we know, compared to the fair and good, compared to the poor, fair and good are this way and that way. So, your reference depends on you. So, the farming system has pastoral, agropastoral, and mixed. If you're going to compare there, we were using pastoral as the reference. So we have to put pastoral first, and then agropastoral, and then mixed. So here, we want it to come to poor first, and then fair, and then good. So we are going to record. Remember the factor, and then levels. Sindio? This is that. So H1 and score, factor H1 and score, levels, poor. So the first one is your reference. Poor, fair, good. And then you check. Tuko sawa? Umecheck? Umecheck? So did it do what you wanted? Sawa? Hello? Are we okay? Yeah. Mko sawa? So highlight row number, kuanzia attitude score. Highlight. Please watch what I'm doing. You're highlighting all the way to number 65. Table, H1, 2, and practices, and run the whole of it. Yeah, that's when nilikuwa nasema muangalie, mtu angalie. Alafu nasema pardon. That's when nilikuwa angalie, uangalie. Mahali umemalizia, I want you to run all those mpaka ufike kwa practice score. Chini. So you can highlight and run all of them at once. Bwana, mwarakisha. I want 3 more minutes. We tufungie hapo. We can do the rest tomorrow. We, si highlight alafu ni kuhighlight alafu natamsha hiyo kitu chini, alafu nafanya control enter ama control R kama ni sisi, whichever you use as a shortcut. We are good? Okay, who has not done? 1 minus P. Who has not done? Tuko sawa? Yeah, sawa. I want you to go back to your data and view H12. Click H12. Angalia kwa board hapa kidogo. We have sorted out the scores and stuff, sindio? Tumezirioda, tuko na no na yes, which we don't care. There's a few like income that we'll work on. There's a couple of stuff. Now, if you go to if you go to organ meat mother, can you see it? That's why unanisikiza kwanza ndio unaenda kwa computer. Uwezi weka masikio hivi ukirudi hivi. Organ meat mother, umepata? Go mbele tu utaona everything is 01 mpaka wapi? Up until like milk products, milk mother, milk products, ndio? Safi? Milk products, ndio? It's 01, eh? I want you to write up on names. Names. That was H1.2, sindio? That's why you listen. Oh, nasema tu he. Aya. Names h1.2. Situleka view h1.2. Now we are on names h1.2. Remember, we know which particular variables were 0, 1. Sindio? So rather than write a code where we are recording one, like mother, ilikuwa mother what? Mother, meat, organ, sindio? Organ, meat, and stuff. So we are recording each and each. We can record several variables as long as they are all similar. If they're all yes, no, or if they're all urban, rural, all of them, we can record them the way we want as a group. So how do we know which rows we are recording? Already we know which ones they are. So this is how we count which column it is. The first column is household ID. The fourth column is this. So child ID is column number 2. Fish, seafood, mother is column number? Fish, seafood, mother. Aya. So tulikuwa tumesema nini? Mother what? Organ, meat. Sindio? Where is that? 20 what? 3. 23, sindio? Na tulikuwa tunamalizia somewhere huku chini kwa meat something, sindio? So we can record, go back to that code now. So, watch here kidogo. This is the last thing we are doing, and then we go. So, we have done view, we have done names. So, names gives us which columns. As long as we know the first one and the last one, we can now do this. Watch kidogo here. Kabla useme he. H13, so we are creating a new data set. So, we are creating a new data set from H12. So, but inside H12, this is a pipe. We can write it this way or ile ya hivi. Sawa. Within H12, we are mutating. Sawa. So we mutate tidyverse across. Please note. Please take note. We are mutating across. Across rows what? Columns what? 23 to 32. Approximate. We are recording a variable 0 is equals to and 1 is equals to, run that code. And you have to be careful that you know which particular columns you're going to work on. So you have to identify them. That is H13. Click view H13. Go to those where we were. And see whether it has done what you wanted it to do. Up to milk products, CH child. Meranio. So we are going to close there today. So what we are doing today is, because of the feedback we got yesterday, we thought if we were to rush through this, you may not understand a little bit, and then when we come into doing the actual analysis. This is a data set that you get. We have actually done like maybe 1,800 to 3,000 lines of code to clean the data to get to where we are. And you can imagine we are still cleaning it by recoding. The data came in different formats. Some people had different data sets. We had to join them so that we get other different stuff. So what we did here was just to give you a data set that is dirty, but then we work through it pole pole. So that at the end of this program, we are able to kind of like see, because you're kind of now working on a data set that was collected, had a couple of aims and stuff. We will do a couple of analyses with a couple of packages. So I've included so many packages so that you can see how they work. They have even packages for making tables. They have even packages for like creating a good table for like odds ratio, like with a p-value that you can just send into like, save in as a Word document, and you include that in your publication and stuff. So tomorrow we start again on diagnostic tests and screening tests and ROCs and other things. I'm not going to ask questions now. I'll try and make the lecture short and do more.